Okay, so you'll manage to build actually fairly good models. Some of you were both in CFI and TLI below 0.05, RMCA below 0.05, and like high scores for CFI and TLI. And we'll move along now to how we can actually plot some of those models. So as you were saying, this is just the equations. It's not actually a nice looking picture which we were getting. And so let me just remove this thing below. And so this actually allows us to visualize and interpret. So it is quite busy, but this sort of shows what we're going on. So what we put in here is to show us the standardized pathways. So in your output, unless you specify that it should be standardized output loadings, there will be unstandardized loadings. You can still interpret the z-scores, but they're not like betas, which you can interpret. So I'm not sure, again, the beamer is not great, but perhaps you can see on your screen as well. But we have speed, visual, text, yeah? We have the covariances or correlations between those three, the double-headed arrows. We also have arrows going to each other, which is the leftover, the trash, so to speak. We have those three loading each other. The one with the intermittent arrow is the one which was constrained or sort of set to be 1. Yeah. Now it will have like a value because we can recalculate everything to get a beta out of that. And you can see, for example, 0.51, I think. Let's see if I can see it here. 0.51, 0.56, so quite some. So how the greener the line, the better the loading. So that's basically it. And so they're also changed in terms of transparency. So unfortunately, the beamer isn't great, but you're able to see on your slides that you have in front of you what it looks like. So it's basically some plot which we used before. Some paths, we feed it the fit object. We tell the plot in a circle. We want it to be a reticular action model, which is RAM, and we tell to plot the standardized coefficients. Now I also said that there would be a different annotation with single-headed arrows. That's the Residuals style, and it's basically exactly the same. It's somewhat clearer perhaps because we've gotten rid of some of the double-headed arrows, especially some of the double-headed arrows going to speed and things in itself. So sometimes people just report this. And so now you have single-headed arrows with the variances pointing to that, and it might be cleaner to show that way. So this is a literal type of layout. Any questions? So it's just a way of visualizing the model which we had before. So that model just with the 3 things, but just here it's plotted all those 3 in the center and just everything lying around. So that's that Holzinger-Schweinfurt model.
How does it know which data to use?
So it's not using the data, it's using the fit object from Lavaan. So it knows that it's a Lavaan object, so that's referring back to the Lavaan object. So you don't have to say data is this, because as long as it has the Lavaan object, it knows what to do with it.
Right.
So there's no further commands as to data is this or data is that. So it just, if you feed it a Lavaan object, it should know what to do with it. Okay, so that's quite nice, and it's quite not nice on this projector, but it's a nice graph to illustrate factor model. Now, you can make a plot of your 2 or 3 factor model, as the one that you just made, via simplot. So it's just taking that fit object that you just saw and trying those commands. So if you just, for example, do this, so you need to load simplot if you haven't installed that last time. And then it will just be a single line of code to plot your model, and that should sort of look interpretable to you. So have a go at doing that. It shouldn't take you too long. So load simplot, and then just this single line of code should be able to do it. You have to install it if you haven't installed it before. And occasionally you might also need iGraph, but I'm not sure if I call it this way. But just simplot should be able to do it. Managed to make a nice little. So those green arrows tell you the loading, so you can see So you might have to zoom in a little bit. Some of them are 0.8 maybe. So that's quite good. That's what we want for factor loads that are quite high. So we'll put the cutoff at 0.6, 0.7, so a little lower. But you definitely don't want things which are below 0.4, 0.3, because they're quite weak. Yeah, so that's the type of layout you would get. Everybody sort of managed to do at least one layout. You manage? Okay. And it's just a matter of clicking on. Just make sure, yeah, it's all fit. Yeah. That should work. Yeah, we'll take a while because it's trying to refit the model. There you go. So those green arrows are the loadings, and you should have quite high loadings, like 0.7, 0.8 or higher on those latent constructs. Okay. Let's move along. So sometimes people would just report this graphically, and then you would have a nice picture with all the factor loadings, and this would validate your model. That's the literal style plot. Now, what you also might want to do is export a table. So this looks quite messy, but it's we called our big friend again is dplyr and stargazer, and what we can basically get is all the parameter estimates from our fit object, and then we can say standardized is true because we want to standardize parameter estimates. So that's just this command. So that's a lavaan command. That's the object for which we fit it. That's telling us that we want standardized rather than unstandardized things. Now you remember the pipe operator. We tell it to only select the things which have this in it. So we only get those loadings. We only want things called, those columns called LHS, RHS, EST, SEZ, and then we rename them automatically. We can already rename them via the select command in dplyr. So latent, we call this latent factor, we call this p-value. So that's basically what's going on there. And so this is, so if you would examine the lavaan object, it would have something called std all, which is just standardized for all, and we would call that the beta. And so that's what's happening here. So we're just renaming the columns which we're going to use in our table, and then we use stargazer to export that results table. So all the loadings that you just saw in the graph, we want those standardized with some coefficients in a table, and it's printed. So you can't see this here. So it starts printing it also to your output in some hideous way. But we can get an HTML type of thing going, and this is sort of what it will look like. So you then have latent factor, so the row numbers, visual, x1, x2, x3. Those are indicators of the observed variables. The B's, the standard errors, the z-scores, the p-values, and the betas. And so those should map onto what you saw in your graph, and those are basically the output estimates. So it's, again, so this is where you can save time, so you can ask R to make formatted tables for your reports, so you can so you have a nice overview of your factor analysis ready. And so that type of chunk of code which I've shown you will take the parameter estimates, rename it, and then generate this nice looking output table. Yeah? Any questions? But sometimes it might be redundant, so sometimes just the figure might be sufficient, but if you also want the p-values and the z-scores and everything, you can get all of those. But those are just ones for the arrows going on the latent construct, so it's not the variances and covariances, because we used this type of because we used the operator to say we only wanted those. So if we go back, because we said only select those which have this type of operator in it. Yeah? Okay, so if we go back to the example which I was doing, most of them load quite high, so above 0.45, so they're quite good. So this is perhaps somewhat lower, like 0.424, so that's not great. But most of them, like 0.85, we're quite happy with that. So quite good factor loadings for some of them, but the occasional odd one, which is scoring lower. Yeah. So that's how more or less how you interpret them. So there's further decision rules on whether you should keep or remove those type of things. So you can now try and remove that item and run it again and see if you get improvements. Some use 0.4, 0.5 as cutoff. Others argue for this range like 0.32, 0.45, 0.55, 0.63, 0.71. So there's all sorts of cutoff rules again to sort of say this is a good item or a bad item. And I've just given, so apply them sensibly because yeah, sometimes there's a huge difference, and it's always the case with cutoffs, like, yeah, keep it in or keep it out. And if you're doubting, then if you're in doubt, usually just report both models, and you can say, you decide, I don't know. Like, so that's also what sometimes happens. Okay. Oh, this hasn't really printed as well as I want it to be, but it's just it's not that important. So the residuals check. Well, perhaps I can still make it slightly better. No. Well, fortunately, I should have make sure that this is not an R thing. It's me generating the output. So what we want to find out is if there's lots of correlations in our trash bags, because that would be problematic. So what we do is this is just a way to take the residuals. So the residuals, if we use residuals fit COV is for the covariance matrix. Those are the our residual trash bags, and we don't want to see a lot of high correlations there. So mostly you wouldn't be able to see because the range has fallen off. I'll try and correct that when I upload it again. So most of the correlations are, it should be absolute size also. Not a bad day, but not a good day. So mostly weak to no correlations were going on here, so that's quite good. So if you find really high correlations, that means that something has gone wrong, and you should go back to the drawing board and see what's going on. So it means that there's some type of measurement error, or two items are really strongly overlapping, and you should perhaps pick one of the two. But most of the time, that's okay. And so this is just ggplot2 core plots, and we do a function to take a correlation and then make this type of figure. And you can study that, and we've done also these type of plots in other ways. It's just another way of demonstrating how to make this correlation matrix. Yeah. So this is just check after you've done it to make sure that nothing odd is happening. If you find lots of really high correlations, you either should model those correlations explicitly, or you should see if there's some way in which you can improve it. What we can then do, which is quite nice, is we can test the model that we just built, this 3-factor model, against the single-factor model and see which one is better. So that's, now I just made one model rather than having speed, textual, and I'm not sure what the other one was, reading, or yeah. What was the third one? Speed, visual, textual. Yeah. So we can then build a single factor model and compare our results to that. So we can then fit that model. So it's just the same type of commands which we had before, but now rather than having one with 3 latent constructs, we just have one single construct. And then again, we get a whole lot of output, but what we can then do is we can compare those fit indices with one another, and so that's not massive output. What we care about most here is the AIC and BEC, because we can compare those to the previous model and then see how much better or worse we do. So lower is better, and then there's certain type of interpretation rules, which I'll come to you in a bit, saying which model is better than that model. So we can basically tally the evidence for one model versus the other model, which is quite useful. So researcher A says it should be 5 factors, researcher B says it should be 4 factors. We can model both, and then we can let the evidence decide which one is the better fit to the data. So there's also a formal way of doing that. So it will have done, let's just make this bigger. Oh, too big. Like this. So it will have printed the same output which we had before. You might already find some things by looking at the RMCA and CFI, whether it's a worse model or not, but we can also use the fit indices. The AIC and the BEC are fit indices. One is Bayesian, which is the B. And Bayesian models tend to penalize complex models more harshly than simple models, because every single arrow you draw is an additional assumption about the parameter distribution or some other thing. So AIC also punishes more complex models, but BEC punishes them even harder. So because it's saying in order for you to posit, let's say, a 5-factor model, you have to have a better theory, so to speak, than when you say a 1-factor model, because Occam's razor and like simpler models tend to be more plausible than more complex models. Yeah. So that's what you need to know about the differences. Sometimes they will point in the same direction, sometimes they will point in opposite directions because they penalize them differently. And then it depends on your theoretical point of view, whether you think simpler models are better models, or whether you, for example, believe in your theory a lot more, and then you might be favored towards the AIC. Lower is better. The rationale for that is information theory. I can't go into too much detail, but everything can be converted to log likelihoods, and then we can quantify that and say how much entropy there is, so to speak, and whether one is more parsimonious in terms of entropy than the other one. And so there are many guidelines on how to interpret those fit indices, but I'll just give you some, which are here. What you can also do is you can generate AIC weights. So you can get the best fitting model and then rescale everything to that model and say this model is the best fitting model and the other one is 20% worse, 50% worse, 70% worse, rather than taking the absolute values. So I'll just show you how to do it with the absolute values, but you can also take the lowest fitting or the best fitting model and then rescale all your models as being a factor of that, saying this one is 10% worse, 20% worse. And those are AIC weights. Yeah. It's just and I won't go into detail to do that. I've put in links for you to click and read out more. You don't have to do that for your assignments, but you should know that these things exist. So some rules of thumb. Again, rules of thumb apply cautiously. So 0 to 2, not worth more than a bare mention. So if you have model A and model B, and they only differ 0 to 2 units, you can't really distinguish between one versus the other. If you have 2 to 6, you would say positive evidence from model A over model B, if model A is the one with the lowest AIC. 6 to 10, strong evidence for model A over B, and then over 10, very strong evidence for model A over model B. Yeah? Does that sort of sound so it's a rule of thumb. Again, it's a gliding scale, and so it's a range 0 to 2. They're not exact. You can see some people put it at 3 to 5, 5 to 7, all sorts of other things. But it's a gliding scale for comparing those models. And those were based on the AIC. What we can then actually do is we can use ANOVA to actually summarize for us the AIC and BEC differences. So we can have ANOVA fit and fit model 2, and then it will print the AICs and the BECs. And it will actually also do, if you really want significance testing, it will do a significance test, whether one is significantly worse or better than the other one. So you can actually see, so this one is, the first one we built was lower is better, so 7. So in absolute terms, these numbers don't make any sense. They only make sense in comparison to other models, yeah? So I can't say if 7,000 is a good value or a bad value unless I compare it to another value. So, but 7,517 versus 7,700, so that's a big difference. So it's over 200 units difference, and over 10 was already strong evidence. So way, way more than strong evidence for the 3-factor model over the 1-factor model. Yeah. If we look at the big, it's somewhat lower the discrepancy perhaps than with this one, but it's still a really high difference. And then we can get a chi-square test because all these things follow likelihood distributions, and we can test 2 likelihood distributions against each other. And that's that p-value in case you want p-values. But most of the time, people do the comparisons based on these values rather than looking at the significance test, because again, it's a gliding scale, and the p-value is just yes, no, significant, not significant. Whereas the other one says moderate, strong, very strong evidence for one versus the other. Does everybody understand this premise and what the purpose is? So you can build a model with 1 factor, 3 factors, 4 factors, and you could say, actually, research group A says lots of evidence for a one-factor model. We went out and tested it. And it turns out a two-factor model is a substantially better fit, so we can discount that theory. So in our case, we have overwhelming support for the three-factor solution. That should be really clear. So that's a much better fit to the data than just having one latent construct, which we would have labeled, let's say, intelligence. So having text, speed, and visual separately was better. So what I'd like you to do is to make a one-factor model for your Sidonius data and compare the fit of that model to not the three-factor, because that doesn't seem to work, your two-factor model, which you just built. And what you conclude, is there better or worse evidence for your single-factor model than for the other one?